Test, test. Bună ziua tuturor! Numele meu este Nic, de la firma ISSCO. O mică prezentare despre noi și după care am să dau cuvântul Christoph, care este unul din partenerii noștri din Belgia. ISSCO, noi avem două business unit-uri, facem software, dezvoltare de software proprii. Suntem din Bacău și deschidem în Iași un birou. Deja am deschis de fapt, dar undeva pe 4 noiembrie am să facem o deschidere, o petrecere de la sediu aici în Iași și undeva până la sfârșitul anul acesta am să avem 20 de oameni la noi în Iași. Proiectele care noi facem sunt proiecte care le selectăm după criterii și după relevanță în domeniul IT. Considerăm că putem să învățăm foarte multe și Sentiance este un partener, un client al nostru din Belgia, care lucrează la o platformă foarte, foarte interesantă, bazată pe machine learning, big data, și care chiar colaborează cu noi pe dezvoltarea asta. Avem 3 oameni în echipă aici în Iași, care și zilnic au ocazia să lucreze pe platforma asta, să construiesc împreună cu ei din Belgia platforma respectiv și vorbim, înțeles, de ajutor și pe partea de arhitectură și de dezvoltare. Da? Am să vă invit, dacă ați găsit talonele din asta la standul nostru, am să vă invit să scanați QR code, să veniți la petrecerea noastră pe 4 noiembrie în sediul nostru nou în Iași. Și în spate aveți un talon pentru un tombola care puteți să completați și la 5:45, când va deveni din nou aici sală mare, am să extragem un castigator pentru un city break care dăm către Belgia de 4 zile, cazare la hotel cu 4 stele. Dacă vă interesează, completați un talon și aveți șansă. So let me now present you Christoph. Like I said, we flew him specially over from Belgium because we consider that the things they are doing together with us are of great value and really also consist of certain important innovative technologies in IT, and I'm sure you will not get bored during the next presentation. So thank you very much, Christoph, for being here, and I hope you have a good time, guys.
Okay. Yep, we lost our screen. Hello. Okay. Good morning, everybody. I understood 2 words, I think, from what Nick said. One of them was machine learning. Okay. So thank you for giving me the opportunity to present to you today. I will start by properly introducing myself. My name is Christoph Liekens. I'm from Belgium, and I am a senior software engineer at Sentiance. Sentiance is for all practical purposes, still a startup, which is headquartered in Belgium. We are a startup which is funded by venture capital firms, and we've grown the past year to about 40 people. Just in my past lives, I've worked in healthcare IT, back in the early 90s when it was still something fashionable to do. In the later 90s, I worked in speech recognition when that was fashionable. And I have also been, for nearly 10 years, the chief architect at an intellectual property company. Okay. So, what's on the agenda for today? Roughly in the talk, you can split it up into 2 parts. The first half, where I'm going to try to explain the Sentiance business to you, what we are actually trying to do as a company. And the second half, I'm going to talk more about the technologies which we use to achieve that goal. So, and in the end, I will also have a few words about our software development process. And I would like to give you also the opportunity to have questions, ask questions if there are. So, the business description, I'm first going to give an overview. And after the overview, it's probably still not going to be very clear what we actually do. So I'm going to actually illustrate it with a number of examples. With respect to the technology, we're going to talk about the architecture of the platform, which technologies are involved, and how we deploy all that stuff. Okay. So if you look at the website of Sentiance, you'll find something like this. Sentiance Sensor Fusion Platform creates ambient intelligence, the ability to monitor and predict behavior for personalized and contextual interaction. That's, well, probably sounds an awful lot like a marketing slogan, because it actually is. So let's try to break it down and see what it actually means. So the first key part is actually the sensor fusion. So we start from taking data from all kinds of sensors. Our lives these days are full of sensors. Everybody carries sensors along with his smartphone. We have motion sensors in houses, etc. You have these healthness trackers on your wrist sometimes. They all produce sensor data. And we capture those data, that kind of data, and use them all together. That's the fusion part. Yeah? And from all of those sensor data, those sensor measurements, we try to, through machine learning techniques, etc., we try to devise some intelligent conclusion based upon that sensor data. Yeah? And the goal is that we can, by those patterns that we detect, etc., build kind of the foundation stones for a interaction with computers, with applications, with websites, etc., with devices, which is much more personalized, meaning tuned towards you, and much more contextual, meaning towards you at the moment you are at the moment. Meaning, it's if you're, for instance, at work, you're in a different context than if you're out somewhere at a music concert or something. So we try to detect those contexts and adapt, build the founding stones for applications which make use and make a better interaction possible with that. So that's basically on a very high level the mission of Sentiance. Okay. Those colors didn't come out right on the projector. All right, so if you look at the phases which we do, is first we need to collect all that sensor data in some intelligent way, because there's a whole lot of sensor data, and some of it is useful and some of it isn't useful. Using that sensor data, we will try to unlock some real-time context of the situation you are in at that very moment. Maybe you are at that very moment commuting to work, or maybe you're dropping off your kids at school. Those are all kind of real-time context which we try to devise based upon from that sensor data. And then the final part is, given that we know which situation you are in, what you are doing at that for a moment, perhaps what you are going to do in the next few hours, we try to provide building blocks to make applications richer and more tuned towards that kind of interaction. Okay. So to make it a little more concrete, this is basically our layered approach to collecting all that data and deriving all that data. You should imagine that from the bottom, there are all these kinds of sensor data coming in. So maybe we get GPS locations from your smartphone. Maybe a motion sensor in your house is triggering. That's all kind of data which is coming in at the bottom. And that kind of describes a moment in time. And we try to enrich those moments in time and we call them events. So what are you doing at that very moment? Yeah? It can be a lot of things. Like for instance, if you sometimes a motion sensor kicked and you're in your kitchen at home, yeah? That's an event. It might be that we detected that you are actually moving from one place to another. Yeah? And by the patterns in the sensor data from the gyroscope and from the accelerometer, and of course from the GPS locations, we can actually derive how are you moving from that place to another. So from the sensor data, we can see whether you're actually using a car as a mode of transport, whether you're on a train, or maybe you're just walking. That's all derivable from that sensor data. And that's basically, yeah, you can be, for instance, you can be stationary at a point, meaning that you're not standing still, but you're not leaving a certain perimeter for a time. We call you stationary, and we try to find out what that stationary actually means. Yeah? By cross-referencing those locations with other knowledge sources, you can find out whether that person is actually at a shop or, I don't know, at a bus station waiting. Those kinds of things are all derivable from the basic information which your cell phone provides. Okay, so once we have those events, you can actually derive higher level information from it, and we call those moments. So for instance, if we detect that you are walking or driving, and your previous location was your home, yeah, and it's a normal working day, it's probably is your commute which you're doing. So we can actually derive that it's most probable that at this moment you're driving to your work, yeah, or you're driving to the school of your kids to pick them up. Those are, again, somewhat enriched and combined, these events, combine them into moments, to get some intelligent information from that basic raw sensor data. For instance, there's also, because there's a steady flow of this information, after a while you can also automatically detect, and the system learns where you live, where you work, even when you have multiple places of work, for instance, just by the machine learning algorithms which you employ. And then we have those kinds of moments, and then we can kind of devise your profile out of it, meaning some characteristics about you. If you start from that information, we can, for instance, see, are you a very social person? Do you come in contact? Do you go to social events? Whatever. Certain aspects of your mobility. Yeah, we can detect whether you kind of what we call a die-hard driver, which somebody takes the car for just about every transport. We can detect whether, what's your work-life balance, how much time do you spend there. And actually the key thing about all those things is that the only thing which we started from is raw sensor data, supplied by motion detectors, supplied by phones. Okay? And that kind of information is actually what we hope will give us the possibility to build richer applications, because they know something about you and they know something about what you're doing at that very moment. Okay? So that's a bit of that's basically the essence, the mission of Sentiance. Yeah? So let's look at a few examples. This is one of our dashboards, and all the logos there are people who are walking around with telephones, on which our data collector is installed, and they all know about it before you ask. So, and we capture all those data continuously, and we kind of built the events out of it, so we can see they are now at home. Every circle represents one of those users. or they are now at work. They are visiting something which we call a frequent location. Yeah, they've been there before, but we actually at this moment in time don't know yet what it actually is. Yeah, or an infrequent location. We also capture patterns, what we call the daily routines, the semantic time. So what is considered a morning routine might start at 6 a.m. for somebody and end at 10 a.m. and might start at 9 a.m. for somebody else. Yeah? And that's how we track activity patterns through the day and try to come up with the semantic time for people. So this is basically, it's divided in lanes. This is what we see now, and this is what we saw in the past from them. Yeah, so we have got somebody at work here. This is the red circle, who is in his morning routine and basically arrived at work using his car because his car was in the past. Yeah. So those are more those event-like things, the basic raw information, somewhat enriched to see what you're doing right now. And then here on the right-hand side, you find what we call the profile-like things which we found out about that user. So we can see that, given that we collected data from that user for a while, we can see that he's actually a workaholic because he spends much more time at work than what we consider a normal working day. As I said, you have die-hard driver. He takes a trip for just about everything. He goes out to restaurants a lot. Yeah, we can detect, we know where he lives. He lives in the city. Yeah, and he's a full-time worker and he's also a city worker, so he's actually got a fairly easy and short commute. Yeah. And basically those are the kinds of profiles at a very high level, what we define, what we derive from all of that raw sensor data. So the key concept is that all of these algorithms, they operate autonomously. The user has not told us anything about where he lives, what he does for a job, whether he has a car or not. We all detect that by our machine learning algorithms based upon the raw sensor data. Okay. This is, maybe it's not very visible, this resolution. This is one thing which we call our fleet dashboard. We have customers and they are interested in usage-based insurance, for car insurance, for instance. Yeah? And what we actually do is we have equipped a number of cars with a beacon so that the telephone detects when you're actually entering your car and starts up the data collection. Yeah? And we then afterwards process all the data to see how was your driving behavior. Yeah? And we kind of divided it up into a number of categories, what we call smooth driving. You get a score for legal driving, and we got a score for anticipative driving. Yeah? And if you see, for instance, this bottom one, he's got very good scores for smooth driving, he's got a good score for anticipative driving, but he's not a very legal driver. He makes a lot of traffic violations. Because we can detect that he's speeding, etc. This one's the other way around. He's perfectly legal driver, but he probably accelerates and takes very hard turns a lot, yeah, and basically does not slow down before crossroads, etc. So he's not anticipative, yeah, but he's perfectly legal, yeah, and that's how we kind of built a driver profile. And obviously that kind of information is very useful towards insurers who want to tune your insurance contract really towards the person. Yeah. And you can also, in that dashboard, you can also drill down, yeah, if you want to see what has actually happened during that whole trip, where the traffic violations were committed. We have a filter here where you can say, okay, I want to see where it really took the right big accelerations or really, really hard braking, because that's kind of dangerous. Yeah. Again, this is all just derived from the gyroscope and the accelerometer data of a smartphone. Then another example, this is one of the, what we call the Internet of Things, more like examples. So we have equipped a number of houses with door sensors so that we can detect whether doors opened or closed, and motion sensors in rooms. Yeah? And that's basically, that raw information is fed into our platform, and after a while we are able to learn actually the topology of your house, which rooms are connected to what. Yeah? And by looking at what time do which rooms get used, we can actually label those rooms, saying, okay, that's highly likely that's the kitchen, highly likely that's the bathroom, and those kinds of things. Again, just by looking at patterns from motion sensors and from doors opening and closing. Yeah. The main application of these things, if in case you're wondering, one of the things which you can do with that is if you've got the normal usage patterns of a house, you could eliminate false positives from burglary alarms, or most false positives. Yeah, because most of the time a burglary alarm, when it goes off, it's a false positive. Using this kind of information, you could say we can try to reduce the number of false positives, because the past patterns in that house indicated that that room will now be used. Okay. Okay, and this is just the display of all those usage patterns, which we automatically detect. Okay, I think that was basically the business context of what we do. I hope it's somewhat clear what it is. So I'll move on to the more technical side of things for the moment, which is probably a bit more interesting. Okay, I hope that from the examples which I've given, that we are dealing with sensor data, with lots of sensor data. Yeah? If we're talking about things like driving behavior, you need things like 25 samples a second of the accelerometer and the gyroscope to be able to do the analysis with an acceptable quality. So we're talking about lots of sensor measurements. Yeah, last evening I actually noticed I made a mistake on the slide. It's not billions per week, it's billions per day. So our problem becomes bigger. So it has all the characteristics of a big data problem. Also because we need to execute all those machine learning models, etc. upon it, we are faced with a deep analytics problem. So it's you can just put computationally intensive next to it. The one thing where we're very lucky at is that most of our functionality does not require sub-second response times. So for a lot of things we do have time to calculate the result. So basically bottom message, this is a big data problem. So what do you do as a startup when you've got a big data problem? Well, you look to the outside, to the world, and see what architectures exist for solving big data problems. And the one we chose is called the Lambda architecture. I don't know whether anybody has ever heard about Lambda architecture? Yeah? Okay, I'll try to do a quick explanation. The point is that basically you model your system according to two pipelines. One pipeline where you could say, I do a very shallow analysis with some very rough results as a first pass, yeah, and already already present these to the user. And in the second pipeline is actually where we do the deep analysis, because we already presented some rough information. We can now take the time to do more deep analysis, which probably is going to take a whole lot longer. Yeah. One of the characters, and so you put everything which you calculate in what is called in the Lambda architecture a serving layer, and you should view this as a pure key value store, yeah, where you don't, at runtime, when the user starts querying the results, you don't want to do big joins or filters or whatever anymore. So basically, denormalized key value stores, everything is pre-calculated. Yeah. One of the key concepts also from a Lambda architecture is the concept of the master data, and the fact that the batch layer always recalculates everything again. So the data connector will make the new data arrive, will append it to the master data, and our batch process, when it runs, will take the whole set of master data into account again and recalculate everything. That has a very big advantage as a startup, that you don't have to deal with errors from the past. Yeah? If you made a mistake somewhere in an algorithm, or you made an improvement to an algorithm, just deploy the algorithm and it will be corrected, because we recalculate everything each time. And that's basically the basic idea of a Lambda architecture. Now, being a startup, we also want to be innovative, of course, so we made our own version of the Lambda architecture. And we made a few modifications. The first modification is that the speed layer, what it produces, the rough analysis you could call it, becomes part of our master data and input for the batch. So there's a shallow analysis here, but we don't want to do it again. So for the batch layer, we consider this as fact, as if it was raw data which came in. Yeah. A frequent criticism you hear about Lambda architectures is that you have to implement everything twice. Once in a limited way in the speed layer, and once in a deep way in the batch layer. The way we try to solve this is that we try to not implement it in the code in those layers itself, but abstract those things away behind microservices. Yeah? So that we can use the same functionality, maybe in a little more limited way, from both layers, and do not have to implement everything twice. And then, as I said, the characteristics of a Lambda architecture are that you recalculate everything each iteration again. Well, we cheat here, because the result of the previous iteration actually is input for the following iteration also. You should view it as a cache. Yeah? It's not necessary, but if it's there, it's a performance optimization. Okay. So those are the basic, very high level architecture of our system. So how does this look as a technology stack? We start here in the top left with our SDK. Our SDK is a mobile. We're talking about the phone data collection here. Is an SDK which our customers can embed in their application, which operates completely autonomously from them. So it by itself, it will decide when it needs to collect stationary data, or when it thinks you're stationary. It will decide when it needs to start collecting sensor data, because due to your movement patterns, you're probably starting a trip, etc. So that gives us all the raw data from the SDK side, and that one sends it to an API. The API is just a RESTful Node.js system, very simple, just for capturing the data which comes in from the outside world. And then you can a bit see the two paths through the speed layer and the batch layer. So for the speed layer, the API puts the data on a Kafka system. So the Kafka system is basically a highly scalable queuing system where you could put multiple listeners, etc., because the speed layer has all the characteristics of a streaming system, right? Then the speed layer, basically for the streaming, we have the storm. The storm, so we use Apache Storm to implement our shallow analysis in the speed layer. And then we go with those results where we talked about the serving layer. For us at this moment, there's a Postgres database where we keep those things actually as simple key value tables, but we use a relational database for it. It's purely for convenience. You can substitute this by any distributed key value store if you want to. And of course, since we are using microservices, we have a Docker system for implementing all those microservices and deploying them. And then, so that's about the speed layer. And then we have the batch layer. For the batch layer, the API puts the data on a file storage system. Because, yeah, maybe the batch run is still ongoing and will be ongoing for, I don't know, 8 more hours before the next iteration starts. So that's, for the batch layer, the new info accumulates there. We use Spark as a framework for processing our batch. So we have long-running batch jobs in Spark. And underneath Spark, we use the HDFS system for storing our master data set. Yeah? Since we did want a distributed, replicated data storage system, because this master data set at some point, yeah, it'll just be too big for one file system. And then we also use Yarn from Hadoop just to schedule all of the jobs from Spark, that they don't interfere with each other, etc. So basically, why we chose all of these components and these technologies is that with these technologies, we hope that we can, as we grow, that we can horizontally scale, yeah, without having to replace a complete system. Now, that's not completely true for the Postgres system, since that's a transactional database, which is obviously has its limits. But as I said, it's purely used as a key value store at this moment, so it can be replaced with something like Cassandra or whatever the fashionable key value store of the day will be at that moment. Okay. And then our API also powers those dashboards, which you saw the screenshots a few slides ago. Okay, then some characteristics. Yeah, I think that talked about most of them. One very important characteristic about our SDK is that obviously we want to collect enough sensor data to be able to do some quality processing upon it. But it's also a balance of getting enough data versus battery life. You don't want to give an SDK to a customer who embeds it in his application and suddenly the user's cell phone dies after an hour because of the battery usage. So that's why we try to make our SDK somewhat intelligent and let it decide, okay, now it's probably useful to start collecting accelerometer data. Well, yeah, if you're stationary for a while, it's probably only useful to collect some GPS location once every 30 seconds or whatever, thus saving a lot of battery life from the application. So, as I said, we use HDFS and Yarn, mainly from the Cloudera distribution. The nice thing about that is that because Yarn has the resource scheduling possibilities, that we can also give our data scientists the possibility to run their custom jobs upon that cluster, upon all of the real data in a distributed way, without interfering any of the production, with any of the production systems. Okay, Some word about our deployment infrastructure. Sentiance does not have servers. Everybody has one of those MacBooks and that's it. So everything is cloud deployed. For the moment, our cloud provider is Amazon. Our main site is deployed in Ireland. It's what we call the mothership. For some customer preferences and legal reasons, we also have a deployment in China. It consists about, I think at this moment, like 115 servers. And we try to reduce costs by using spot instances on Amazon. I don't know whether everybody knows what spot instances are, but basically it's a machine where you give a bid price and then you get to use the machine. But if somebody has a higher bid, you can lose the machine within a second. Yeah? So by just making sure that we have enough redundancy and failover in our system, we are able to use spot instances for a large part of our infrastructure and thus greatly reducing the costs of running everything. We use the Amazon RDS for our database functionality, and we use the Elastic Container Service from Amazon for our Docker management system. The important thing is that although we use a number of Amazon cloud-specific technology, there is no real deep coupling to Amazon. RDS between the top layer is just a Postgres database. You can run it on everything. Yeah, there's the container service. There are other container management systems. If you stick, the important thing is what is in your Docker services. Yeah? So we try to make it ourselves a little bit easier by using those services, but make sure that we don't have a too hard coupling to the Amazon system. One of the reasons is that some of our prospective customers, we don't do at the moment, but own their own data center and probably are going to want a deployment in their own data center. Okay, so that's our deployment. About our software development process at Sentiance. If you look at the staff at Sentiance, it's roughly divided. The IT staff is roughly divided in 3 parts. We have the data scientists. Those are the really smart guys who stare at sheets full of sensor measurements all day and try to build a model out of it and come up with algorithms, etc. And then we have the data engineering part, which is less smart than the data scientists, but they work harder. I'm part of the data engineering, by the way. So they take whatever the data scientists come up, and it's not such a hard boundary, but this is about it, and try to build a platform out of it. Yeah? So we get algorithms from the data scientists, we get models from the data scientists, and it's the data engineering's job to build it out in a platform that runs 24/7, that runs reliable, that's maintainable, etc. The mobile engineers, the ones who built the SDK, are also part of this data engineering team. And then thirdly, we have what we call the solutions team. Those are the guys who actually built the dashboards, etc., which you saw a few slides ago. And we basically do the technical interaction with the customer and the integration with the customer system. Some customers might require that they get a daily offload in a CSV file. Very simple. Other might want to be notified through a WebSocket or a queuing mechanism or whatever. And that job is handled by our solutions team. Although there are 3 different teams, each with their own focus, we operate as one DevOps team. Yeah, meaning that the whole team has joint responsibilities in all those areas. We do our own platform building, so we make our infrastructure on the Amazon. We do our own releases on that as a team, and so everybody of the team needs to be able to do that. And we also do our production support as a team. Yeah, meaning also everybody in the team is involved in production support. Even when you're a data scientists are expected to write production quality code if they write code. If it goes wrong somewhere late in the evening, they get a call. So it's a real DevOps team where everybody jointly has the responsibility of keeping everything up and running. Yeah. Now, obviously, there's not 500 of us, so we try to automate as much as possible. Yeah. So we are big fans of Jenkins or whatever CI system you can use to build our software, to test our software. We have jobs where we actually build releases and release to the production system from a Jenkins job, etc. We are also big fans of the principle, and I hope I'm going to say it right, infrastructure as code. Yeah. So obviously, because of these spot instances, we need to be able to rebuild complete machines very quickly. But if you lose them, and for that we use the Ansible system. Ansible is something similar to Chef and Puppet, for those who know Chef and Puppet. It's where you actually write code to do your server provisioning. Yeah? And that allows us to just quickly spin up new servers in case we lose one, or in case a sudden big load of data comes in. So we're also big users of that. And then, well, the final part of our methodology is, since we're processing billions of sensor measurements a day, please be careful with the code you write. If you make a performance mistake in one of the core routines, yeah, it could easily cost us 10, 20 machines, which we need to put extra in, which is obviously very expensive for a startup. So we put a lot of effort into optimizing our code, and just from the pure algorithm view side, you try to use the most efficient Java and Python language constructs possible, try to optimize our data structures for performance, etc. Okay, I'm out of time. That's all I wanted to say, actually, so I'll be happy to answer questions if there are. Yeah, go ahead. Sorry, I'm gonna come a bit closer because I can't listen. So what happens is that the data is collected on the phone, for instance, through the SDK, and certain types of data are sent directly to the API, RESTful system, and then to Kafka. Yeah? That's basically the small data chunks, you could say, a GPS position every minute, those kinds of things, not a lot of data. Obviously, if you have a trip data, which might, you have driven your car for 2 hours, then you've accumulated quite a lot of sensor data. This can easily run into the megabytes. Yeah? And we actually don't want to push that through mobile data, because obviously it consumes your mobile data plan, and it also consumes a lot of battery. Yeah? So we actually buffer that on the mobile phone until the user gets on a wireless system, and then it gets transmitted again to the API, which puts it on a Kafka system. Yeah. That is done all by our data scientists in Python using SciPy, NumPy, Theano, all those, well, the standard things. Anything else? Yeah. Because we were young and inexperienced. Because we were young and inexperienced. So it was basically, we started from nothing, and we read the big data book. And that was basically one of the first recommendations to use there. Are we totally happy with it? Spark has a lot of weaknesses and a lot of strengths. Yeah. One of the weaknesses is that if your code is not perfect, you're very fast into memory tuning hell. Yeah. So we're moving for certain functionalities away from Spark and more into the streaming area like Storm. And for other things we are, well, we know a little bit more about Spark and we're tuning our code to make our jobs better actually. Well, at this moment we are not reconsidering to move to anything else, but since we're a startup, we still have the freedom to move between technologies. So if there's a very good reason, we will certainly do so. And we try to also make our technology dependencies kind of limited. That we, I mean, our core competence is in the machine learning algorithms and so on. So we don't want to be the firm which has the best Spark programmers in the world, because that's not our core competence. Yeah? And as such, we try to kind of limit our dependencies on such things and know where we can move to other things and where not. Yeah. Anybody else? No. You were first, I think. Yeah. Mm-hmm. Mm-hmm. Yes. Mm. Yeah. Okay. So with respect to the first question, it's a joint responsibility, meaning we're a small team for all practical purposes, and we make agreements amongst ourselves about who does production support that evening or that night. Yeah? And it's, I mean, it's a luxury which a startup has, which a full enterprise company doesn't have. There's a lot of goodwill. Yeah. So it's mostly based on team spirit and rather than on agreements and structure. Okay. With respect to, you also asked about a user which does not know how to use this. Yeah, that's the responsibility of the solutions team, actually, to interact with the users. That's their responsibility, yeah. And then with respect to your question about code quality, yes, we use code quality tools to a certain extent. On the Jenkins jobs, like where you do the standard things, your code coverage tests with Cobertura for Java, for instance. We have PEP8 analysis for the Python code, but not further than that at this moment. So we don't actually do automatic complexity analysis or whatever. Which is on the roadmap to do, since we are growing, and at some point you need to do such things, but it's not used to an extensive amount for the moment. Okay. I thought there was another question here.
I was curious, can you name some names of your clients and how they use it?
No. We are a business-to-business company, meaning you'll never see our name on an app. You should, for the customers, I mean, I'm not allowed to name any names, let's be clear, but you should view them in the area of the world leaders in consumer electronics, world leaders in mobility, those kinds of areas. Yeah. Obviously, we have smaller customers also. There are, in Belgium, insurers, which are our customers. But those are really smaller things. But we are also working with big companies, yes. But it's all anonymously, we're all in the background. Okay. I would assume I'm completely out of time for the moment. Okay. Thank you very much for listening to me.